Like you're sharing as shared by my teams.
Okay.
Okay, thank you. Apart for this technology issue.
Yeah. Sorry everybody for the late start and the technical issues. But this is SenSiteUQ intelligent sensor placement for smarter sewer systems. So the real problem we wanted to tackle here was pollution and flooding. If you've checked the news, you might have seen water companies are having issues with untreated sewage and going into the environment and causing problems. The regulatory bodies have increased the fines, and action still hasn't been meaningfully taken, and the issues persist, which kind of alludes that this is not a willingness problem, but more so a technological problem. Because with the financial penalties, they have strong incentive to do better, and they're not able to. So here we're going to try to apply technology, applied mathematics, and applied statistics to help water companies do better. And here you'll see a little toolbox emoji. Through the course of the presentation, I'll be showing you some tools to add to your toolbox and consider when dealing with water networks. A little context about the project. This was done through the Off-Watt Innovation Fund, which is the regulatory body. They saw these issues and they put some money on the table and asked companies to come up with some technological solutions to make the water companies, to aid the water companies and make the network smarter. And we proposed SenSite, which you'll see, and we were lucky enough to win and got the chance to develop this tool further. And who are we and why did we get this honor? We're digiLab, where we focus on uncertainty quantification and AI. We were born out of the University of Exeter right here. I believe it was the Applied Mathematics Department. They got the lucky rebrand of becoming AI all of a sudden with the boom, and then became quite profitable. So then it spun out and became its own company. And again, focusing on explainable AI and solutions that people can trust. And with the focus on uncertainty and explainable AI, we've had the opportunity to do many projects in many risky areas, such as environment with reef restoration in Saudi Arabia, and water companies, and fusion energy, material science, and aviation. And we have some experience in the water sector, which helped our expertise and gain this honor. Our first project actually was with Southwest Water, and they've been a core partner as well as some other water companies throughout the process. And who am I? I'm a machine learning engineer here at digiLab and technical lead of projects in sensor placement and control, particularly in the water sector and nuclear fusion. So our solution to the problem of pollution and flooding is to provide insights into the wastewater networks and suggest optimal sensor locations, given their hydraulics models and historical data. If they can detect the blockages and issues early, they can prevent them from happening, and we can get less pollution and flooding. We tackled this problem with three major pillars: convenience, risk, and importance. Firstly is convenience. There's just some locations where you can't place your sensor. So what we've done is created a tool to automatically identify inconvenient locations for sensor placement. This is generally with roadworks, where you can't access manholes with too much traffic or that's in the middle of a junction, and they would prefer to place sensors on areas where you can easily maintain and place your sensors. And now getting into the main drivers is risk. And we want to perform risk analysis by examining past events and using those past events to help predict areas where future occurrences might happen. And this is mainly done by leveraging probabilistic models, which is our first tool in the toolbox, where you have some historical data and you use that historical data to build these probabilistic models, which essentially has a distribution function of where events will occur and creates a smooth, continuous space to help predict where issues will happen. So here's an example network with our key points of pollution and internal and external flooding, given incidences in their in the recent history, we were able to build a mapping of hot zones to focus for sensor placement. And when you're dealing with multiple events, it's helpful to be able to compound them in a realistic way. But thankfully, with the regulatory bodies, their financial penalty kind of gives you the importance of each type of event. For instance, pollution events, they have a bigger financial penalty, so you weight that higher, and so on and so forth. And you're able to use that as a weighting function to say, if pollution's not that common, but it's worth more, maybe using that to consider things. And then moving on to our third pillar, importance. So we have our risk, which is data-driven, and we have our importance, which is model-driven. And this really comes from your hydraulic model and hydraulic simulations, which is our second tool in the toolbox. So water companies generally have these big models of their water network that they use for analysis, and we can leverage those to determine the high throughput pipes. And those ones will be more important, and importance is tied to risk here, as if lots of water is coming through a pipe, it's important and very risky. If a blockage happens, it can cause many upstream problems. And through running hydraulic simulations, you can identify these key pipes which will have the most flow. And then you have your important manholes, or nodes. And here we're concerned with manholes with high network centrality. But what is network centrality? What's a central node? Here, graph theory comes in, our third tool in the toolbox. So lots of clever mathematicians have come up with graph theory and surrounding algorithms, which is structures of nodes and edges. And it's basically a way of showing how things are related. And here we have our pipes are our edges, and manholes and water treatment plants are the nodes, and kind of have an idea of how the networks are structured. And there's some pretty cool algorithms that get unlocked to analyze features of these networks. And the key one we focused on here was node centrality. With this example, it's a small toy problem for easy to visualize. Here we have two rivers in a small little section there. And from these hydraulics models, we've built a tool that allows us to convert your hydraulics model to these mathematical objects or graphs, which allows us to quickly use proven algorithms, and we can analyze these features. So here we're concerned with node centrality, because if a node is central, it has many things coming into it, many things coming out. So issues on central nodes will cause larger problems throughout the network. And with our example here, we have our centralities, with being lighter or more yellow is more central. And it's kind of intuitive, as you can see, the most central node has many pipes coming in compared to the rest. So if a problem happens there, then water will be backed up along each of those. But that was kind of easy to do. We could have maybe eyeballed that. But the real power of these optimized graph theory algorithms is for fast analysis of large networks. And we're able to do centrality analysis over many functions. And this is in the tens of thousands of nodes, this one on the right, and this was done within minutes. And some of the powers of these AI-powered tools are being able to do things faster than you could without them. And it would be quite infeasible to do this kind of calculation by hand. And now we have to bring together our three major pillars of convenience based on land use, risk based on our historical data, and importance based on our network models. And this brings us to optimisation, which is another tool to add to your toolbox, where we have these few objectives, and you combine these objectives to create a score for importance and risk of each node, each manhole, and then you can weight these nodes based on how close they are to another one. For instance, an area with high risk, there'll be the highest scoring ones right next to each other, and we might not gain much extra information by placing sensors next to each other. So then you downweight based on local regions, and then you have some optimization algorithms that maximize these importance and risk functions and get you a network that is well covered and gives you information about risky areas and important nodes. And again, this takes minutes, and talking to our partners, they spend months creating their plans for sensor placement. So this really helps iterate and get sensors out faster, get data in, and address the problems that they're facing with flooding and pollution. Going back over our toolbox, we have probabilistic models, which are our bread and butter at digiLab. Probabilistic AI, determining probabilities of things based on past events, and leveraging hydraulic simulations to determine features of your network, and also generating some data from those hydraulic simulations to use in your analysis. Graph theory to understand the core features of your networks, and optimization to take your analysis and get something actionable from it. And if these things interest you, we'd be happy to join and do some collaboration, but I would consider the problems that you guys are working on and seeing if any of these tools can help you out. And we're always here to help if needed. Any questions? Yeah.
Something you haven't mentioned in those tools is the possibility of being downstream of an area that's highly likely to block, such as poor condition pipes, tree root incursion, or fat soils and grease. Does that come into it at all?
Yeah, so this will be in our probabilistic models.
Ah, okay.
Yeah, so
Yes.
normally when you just look at each node one by one, you'll have some nodes that are high risk, but then by creating a continuous space and a smooth function, you'll get all the nodes surrounding that node as being high risk. And yeah, because that's a good point. If you're just focusing on the one with the problem, it'll be downstream that feels the effect, yeah.
Yeah, that you want your sense. Okay,
Smooth,
thank you.
smooth probabilistic distribution solves that.
Thanks for the presentation. I have a couple of questions. One is regarding you are using multiple data sources like historical data, hydraulic simulations, and other aspects of optimization as well. You take one of those out of the picture, saying for those utilities who doesn't have a work order history or so, or else an accurate hydraulic model, how will it impact your sensor placement results?
Yeah, so that's a nice question. Thank you for asking. And this is an advantage of having three different pillars, because if you lose one, you still have some information from the other two to make your decision. And these are kind of like multiplicative, multi-objective optimization. So you might have a worse sensor placement with fewer information, but comparing to the ideal, it's worse. But kind of like comparing to the humans, if we don't have hydraulics models, we can't do that analysis, period. So then we just do driven based on data. And you use what you have to the best of your abilities is the advantage of having multi-objective optimization.
And the second question would be, you are using centrality as one of your objectives. What are the edge weights we can expect there while calculating this?
Yeah, so the edge weights will come from these pipe importances. So if a pipe has high throughput, the weighting of the edges comes from a normalized value for these pipe importances. And then that gets used with, and then convenience kind of informs the node the node weights. So if an area is quite inconvenient but not impossible, you just downweight that node. And that allows you to, in your centrality, get information from pipe importance and node convenience.
When you're allocating sensors, do sensors push other sensors away from them? I'm assuming that once you've placed one sensor down, maybe it changes the weights, the edge weights you're just talking about.
So this is the need for optimization. Because if you're just looking at a table of values, then you could just select, oh, these are the best ones. But then it's not considering that, yeah. So anytime a sensor is placed, it downweights by how far. And that's an advantage of building these graphs, is you can get distance that's not geographical distance, but network distance. And that's what we use to do the downweighting.
And is that a kind of greedy algorithm? You'll take the top one on the list of the most valuable node, and then you'll remake the list on the basis of having that one node and do it again?
Yeah, we've developed two different methods. One is a sequential greedy algorithm, and then which has two different parts. One where you always select the best, and then one where you give a probability to select each, which is weighted by its individual importance. And then we also have genetic algorithms to help with that.
And the graph theory, are you using neural networks? Is that something you're exploring?
Yeah, we did a bit of exploration into that, but we found just traditional graph methods did the trick. Yeah.
There's a question online. So how do you evaluate the probability model?
The probability of events occurring? Was that the question?
Yes. How do you evaluate the probability models?
Yeah. So there's different goodness of fit measurements that come in with each model, and basically saying, so you have your data and you fit the model, and then you have a metric that says how likely is it that this model produced the data that you've got, and that's the metric that we use.
So on this map, you have those density functions. Are they purely based on the number of occurrence in the historical data?
Yes. So we build. So imagine that you have a space and you're dropping balls on the space, and those are the events where the balls land, and we're kind of fitting how the hand moves.
My question is that do you also consider the severity of the events? So there's some of the locations that might have more deeper flooding, for example, and all the other components that's contributing to the map.
Yeah, that's a good question. Ours is driven by the financial penalty. So for this one, it was just doesn't meet the criteria of the fine. And that's data that these companies have readily on hand and is really easy to quantify. And it might be a bit tricky to quantify the issues of a big event versus a small event when you're not using fines. So yeah, it's basically all the pollution events were where they got fined for pollution, and then you weight the severity of pollution by how much the fine was.
Okay. So in other words, could those be replaced by others? For example, number of population being affected by the event,
or volume, estimated volume spilled, or number of people.
Yeah, Ben?
Have you considered maybe using a 2D model as well to add to your three pillars? So you've got the 1D model, which is getting your throughput on your main pipes, but a 2D model, I'm especially thinking in terms of flooding events of the past. 50 years ago, we maybe didn't have as many buildings as we have today. Urbanisation changes where the water goes and how much water there is, so we might have more flooding in new places. And hydraulic model might be able to anticipate where those things are happening. 2D modelling is a factor of that. Is that something you're moving towards?
Yeah, so the edge importance came from these 3D models, from InfoWorks ICM and such.
Okay, so does it have a topography surface? So we've got surface flows and pipe flows.
Yeah.
So normally we'd say a 1D model is just the pipes, a 2D model is the surface. That's terminology maybe there. Okay, so you are using a surface model as well.
Yeah. And that was given to us by the companies.
Yeah.
They use these 2D models, and if they provide us with their simulation, their model,
and
we run it for this. Yeah.
That's for the throughput on the pipes. Have you used those models to maybe predict where flooding events happen to add to?
Yeah. So that is a good question. We did consider it for the cases where you don't have historical data.
Yes.
Because I think when you have historical data or recent data, you should consider that first, because there will be some simulation to reality gap where these models, these hydraulics models, won't be perfect modeling of what happened, and I believe data will be closer. But in the absence of data, yeah, that would be good to run your rain scenarios and see which ones are most likely to have issues. Because lots of times for these flooding events, it's caused by things that are difficult to model, like people flushing diapers down, and yes,
Wet wipes is the other big one there.
proximity to fast food that pour oil down the drain kind of thing. And those get captured in the data, but not the models.
So, as it says here, so probabilistic models are built from historical data, presumably at least a couple of decades or more, during which periods both the catchment characteristics change and possibly, well, pipes get, well, the torrid, and then you have possibly some reconstruction in the system, extending the system. So how do the models take changes in the system setup in the historical data, and how they think of those, how they take those into account looking into the future, potentially urbanization?
Yeah, so one key advantage of probabilistic models is how data efficient they are, because they're not finding a one-to-one mapping, but they're mapping a probability distribution. This was done, I think, only on 2 years of data. So then once new data comes along, you can input that data and build new models focused on your new conditions rather than old, outdated models of your network.
Yeah, David?
So where have you got with this? Have you got examples where, on the advice of this, you've gone out and placed sensors, and how has that gone?
Yeah, so we have placed, I think we have about 50 sensors to place. They're currently in progress. Half of them have been placed so far.
Okay.
One of our key metrics for convenience in particular was success rate of placement, because that's something that they spend a lot of time on, and there's lots of random issues like a car's parked over the manhole. And before using our tool, they had about 33% success rate of going out to a place and placing it. And we've hit about 65%, so significant improvement. But yeah, through the process we've seen that this is a big issue. Even with getting 65%, it's a lot of back and forth when they say, oh, we couldn't place it. And it's still in progress.
What types of sensors you are looking at here?
I believe these are head and flow. So measuring, so it's in the manhole and measures the height, the depth. And our flow sensors are another type that we've used in the models.
Ramesh, would you want to ask your question online?
Yes, thank you very much. Thank you very much for your presentation. My question is actually about that you have your probabilistic models. As you use the historical blockage, the failures, or whatever it is, and then you have to evaluate it somehow. So you should have some kind of test data or validation data. The question here is, how do you validate it, or let's say, how do you test that to see that the probability values are all right? My question comes to the point that your model is working temporal. I mean, you are using the historical data and you are testing with the more recent ones, or it is just a random split in your data?
Yeah, thanks. So our data is basically any event that's happened over the past 2 years. And for this, as I said before, one of the two things we do is measure how likely our data came from the probabilistic distribution that we've fit. And we'll do that on data that's already been trained and hold back a few.
Thank you.
It's a bit different with probabilistic models than traditional machine learning, where you would measure accuracy, or regression, where it's how far away was your guess and probability. Whereas this,
Yes.
you're basically fitting a probabilistic function. So
Yeah, that's my point actually. So
Yeah.
digiLab said that is the explainable AI, so you couldn't go with the traditional metrics to show that this is working or the accuracy or something. So I was thinking that if you're going to auto company and you're using your probabilistic models, how you evaluate them or how do you show
Yeah.
that they're working?
Yeah, so we could say, like, this internal flooding model has the data that we have, there's a 99% chance it came from the flooding density function that we fit, or something like that. I don't have the numbers off the top of my head, but that's how we would approach that with these probabilistic models.
Thank you.
Thanks.
More questions? David?
Sorry, keep asking questions. Is the point of the tools that you're using to have optimal placement in order to predict blockages or spot blockages as they've happened? Or is it to predict, or best predict, overflows?
So because of the weighted compound density function, it's to minimize fines.
Ah, okay, thank you.
And then
Yes.
so we rely on the regulators
Yeah.
to have good fines that are based on how much it impacts people. And then it works both ways, because as a company, like selling to other companies, they're interested in saving money. And yeah, it works well with regulators, companies, everybody involved to do it that way.
Have you considered shaping your probabilistic models by topography and where these networks are pushing the flow? Because the downhill, for example, is influenced by events upstream, but the upstream is maybe not influenced by events downstream. So I could imagine that if you had just the surface might be sufficient if you assume equal depth of cover, but that's not true yet. But you've got the hydraulic model maybe, so you've got the invert levels. You might be able to figure out which bits are upstream and then use that as an additional shaping on your maps of probability.
Yeah, there's actually a few things we've considered to add to this model. Another one's like pipe size and also pipe material. There's some materials are more likely to have issues with like the really old, like how old the pipe is. And for this one, we just considered location. But definitely as an extension, we've been looking at what other features might be useful in assessing risk. And thank you. We'll prioritize that.
I'm sure you could add it on the graph, for example, for that. It's an easy kind of edge attribute. You just, is it upstream, downstream? Is it a
Well,
material?
in the graph we do have directional, but then no idea of the gradient, because I imagine,
Might be
like, considering the 2D and depth of pipes as well.
Pete?
In your problem statement, you had that one of the goals is to help address flooding,
Yeah.
pollution and flooding. So how does knowing where we can put sensors link through to reduce flood risk?
Yeah, so working with our partners, we've kind of been discussing this a bit, is if they notice that the flows or the head has been increasing and the levels have been increasing, that might indicate that there's been a blockage. And you can go out and treat that before it happens, is the idea with sensors, is to gain information about the inner workings of your system and what's going on, and being able to detect anomalies.
How does that link to flooding then?
So flooding might be backed up blockage. So especially the internal flooding, some pipe junction near your house gets blocked, and then everything you flush down goes back up into your yard.
I had a very similar question, and so I suppose specifically, what is going to happen to the output from the sensors once they're placed? Because design of where they're placed is a bit dictated by exactly what's going to happen. Are they going to feed into a SCADA system? How are they going to be monitored? And what sort of thinking is going behind the monitoring of those?
Yeah, so our data from our sensors are shared with the industry partner in the city where they've been placed. And right now they have their own methods, but we're using the data that we've got and going to propose smarter ways to partner with them.
I thought you might be. Yeah. Good. Okay.
So, Brian?
So
the pollution, does that include both pollution caused by blockages and by combined sewer overflows?
I believe so, yes. And anything that they got fined by. In their historical data.
Not just asked so similar what been asked earlier. So for now we have a student is also working on similar ideas that's looking into the criticality of the networks. So which node is more important than the others, and also that's looking into the different networks. So it's not only the water, wastewater network. You might have the road network, other electricity network. So how do you think in your approach can be used, applied to link those different elements and different networks together?
Yeah, so we also have a more general sensor placement tool that we've been using in our reef projects and placing sensors on nuclear reactors. And that's based on how much information is gained by a sensor. So you have a big database of simulated sensor readings. So if the student's able to do some simulations, if there's some electricity, good modeling software, and develop a big data set, and then they'll pick sensors which can best distinguish between each row of the data. And that's the fully data-driven approach, which we've been working on.
Yeah, and also that the placement of sensors based on the importance in the network. Could that be the case? It's not placing the sensor at that most important node, but it's upstream of its surrounding to detect the issue that might be coming, rather than the one that's most important. When it fails, it causes big disaster, but when you detect the signal there, it's already too late.
Mm-hmm. Yeah, so it could be, it's a good point that we could add to, like add upstream. If you take each location of an incident, instead of considering where it is, how we do it now, consider the location, and the smooth mapping will catch upstream and downstream. One thing that I think we're hearing from multiple people here is kind of pushing that focus upstream a few, and rather than considering the important node where the problems happened, is put it upstream where you can detect it first.
Yeah.
Thank you for your presentation. Excuse me, I have a question about your data acquisition system. When you record your data with your sensor, are you recording the data on a SD card or send them via Wi-Fi to the servers?
Yeah, I think it's from, like, they have little SIM cards, and they get sent through, like, email, like, Wi-Fi, through data, like 5G. Oh, yeah, that answers your question. Yeah.
Have you learned anything about, it's interesting that it's driven by the level of fines. Has that taught you anything about the fining regime, about whether that drives, kind of curious outcomes? Like, I mean, are they finding more for a CSO spill than an internal sewer flooding, for example? I don't know what the levels of fines are.
So pollution is an order of magnitude bigger than the rest.
Yeah.
It kind of goes in this one, you have pollution, which is maybe 10 times more than internal flooding, and internal flooding is maybe 5 times more than external flooding. And then this creates interesting scenarios where this is a non-coastal region, so it doesn't actually have that many pollution events, or where it's going into local water sources. So as you can see, the compound function, which is weighted by fines, is more heavily weighted to internal flooding. And so with this way, you'll be able to see in each network and target what happens more and how they get fined most in that network.
Yeah, you could imagine a catchment where the emphasis then becomes on some combined sewer overflows and less on someone who's suffering repeat internal flooding, for example.
Yeah, if it's just one person who's,
right.
yeah. might be interesting to maybe, I guess it gets weighted higher because there'll be more instances in the data set. So I don't think that one person would be left high and dry if they get repeated events.
Thank you.
Yes, Pete.
So I know you're in. This was an off-what project. How have you found the discovery challenge as a program? Have you got any reflections on that?
Yeah, it's been nice because they hook us up with an industry partner, and this would be really hard to do without them. Water companies are particularly very hush-hush about sharing their models, and developing the tool before the Innovation Fund, all you could find was this small toy network, and it was really nice to get access through the industry partners that Ofwat set us up with to be able to test scalability and seeing if we can do this on a huge scale, which is very nice.
So something you're probably already aware of is that there are already sensors out there, especially on CSOs and event duration monitoring and stuff like that. It's obviously mandated by the regulators. So does your solution allow kind of inputting a list of here's a bunch of sensor locations we already have sensors in, and here's how you want to supplement them to best solve the problems of tomorrow, etc.?
Yeah, using that downweighting we discussed before, where if it's one step away in the network, 2 steps away, you decrease the importance. Our industry partner did give us their whole set of all their sensor locations, which drove this recommendation here. They can input all the locations.
Always find another place to put a sensor, I assume, until you run out of manholes with that kind of methodology. Is there a point at which you say enough is enough and we have enough sensors and we don't think we're going to get any more benefit from adding sensors?
Yeah, that was our first thought, was to show value in this tool would be to say you can save money by having fewer sensors. But the way most of the companies operate is they get a budget for stopping flooding. And it's okay, let's spend a budget on sensors. So oftentimes you might get a situation where you have 50 sensors, place them best, rather than trying to save money. Hopefully that changes in the future once these networks get more full and be able to do analysis on when enough is enough.
More questions? If not, I think it's good. Yeah. Okay, I think it's good time to close the session. That leaves us time to move to the other building for lunch. So could you please join me to thank for Ethan's talk?